Hello, welcome to Red Hat Enterprise Linux 8 System Administration from Kabuga Labs. I'm Charles Kabuga. We are still on introductory topics, and in this lesson we are going to have a bird's eye view of Relate and where it fits in the operating system stack. In a sense, to appreciate the complexities of an OS by looking at the kernel. Now, regardless of the operating system you are using, be it Windows, Linux, Android, iOS, you name it, a portion of it is always in memory and running all the time. This is the kernel or the heart of the OS, and it has the most frequently used functions such as CPU scheduling, that is which process can access the CPU, when and for how long. Memory management determines the share of memory given to all the processes. There is hardware device drivers, file system management drivers, handling interrupts, network management, that includes network protocol stacks and network devices, amongst other bits and pieces. So, an OS is made up of this core plus other useful utilities packaged with it. These other useful utilities are collectively called user-level programs such as word processors, media players, browsers, video games, just normal programs that we interact with on a daily basis. Because the kernel cannot work on its own. It needs them in order for it to function. You can liken it to a car in which you have the engine as the central part, but you also need other components, the wheels, battery, seat, chassis, in order for you to have a functional car. With that, there are generally two types of kernels. One is monolithic kernel, in which you have all these functions we mentioned above cramped together into one large file, hence the term mono. Everything that goes into a kernel is pre-built into it, and this results into a large kernel that has to entirely be loaded into memory, even for functions that are not currently in use. If you happen to have a device driver not included, then this kernel will not work with that device. To add the driver, you'd have to rebuild the whole kernel, which would be difficult to do without breaking or damaging the kernel. And if any service were to fail, it would lead to collapse of the whole system. However, be that as it may be, it has very admirable features. One is that it is essentially a single large process that runs entirely in a single address space. And this allows all components in the kernel to have access to all of its internal data structures and routines, making execution quite fast. Also, monolithic kernel provides its services through system calls which are simple and secure. And the other type of kernel is the microkernel. And in this type of kernel, only a few essential functions are assigned to the kernel. These functions that you can't do without are memory management, interprocess communication, and basic scheduling. All other OS services such as file systems, network protocol stacks, graphics, device drivers are all provided by processes called servers running in the user space. And these servers may call other servers through interprocess communication to request for services. That is, in case one server needs the services of another server. And if one of the servers were to fail, it can easily be restarted without affecting the whole system. Failure in this case is isolated only to the server. And it allows for a flexible implementation since the server may be customized for a specific environment. Expansion here is easy because all you need to do is add a server without disturbing the kernel or even disturbing the other servers. This architecture is small and isolated and can function better, at least in theory, because process management can be very complicated, especially when you're having interprocess communication you have to manage between different processes. So, that begs the question, what type of a kernel does Linux use? I pose the question to you. What type of a kernel would you want it to have? Either monolithic or microkernel? Although Linux may be generally considered monolithic, it achieves most of the potential advantages of a microkernel by use of a modular architecture. Modular architecture uses modules, and modules are pieces of code that can be dynamically linked and unlinked directly from the kernel at runtime to extend its functionality. And the kernel automatically detects the need for a particular module and loads or unloads it as need be. You don't have to do it manually, although there are ways to do it. The module does not execute on its own, rather it is executed in the kernel mode, meaning it becomes part of the kernel. User space programs request for kernel services through system calls. To illustrate this, we can start off with the master functions in the kernel. This is the core of the most frequently used functions. The scheduler, memory management, such. This region here represents the kernel space where we have the single address space. And out here we have the user space where things like browsers, text editors, graphics are running. This boundary represents the system call interface. It is the line of communication between user space programs and kernel space programs. In the kernel, we can have some modules loaded like the net filters for the firewall, network drivers, and maybe a few device drivers. This is the state of our system at the moment. If you plug in a device for which a device driver is not loaded, the respective module is automatically loaded while the system is up and running and becomes usable. If you decide to do virtualization, all you need to do is load virtualization modules, which is done automatically for you by the kernel. If KDE or GNOME clashes, failure and vulnerabilities are isolated, the kernel is protected and other users are unaffected. No wonder viruses in Linux are very rare. Not absent, but rare. Modular architecture allows for customizing Linux to a very specific use because all you need to do is remove and add modules as you wish. If maybe you are going to use it in embedded systems, probably you don't need graphics modules, net filters, virtualization, and most of the device drivers, making it very lean. Although we haven't installed Red Hat, let's have a lab to demonstrate what we have learned so far. First of all, let's see how to verify the kernel that is running in the system. I'm going to log into my system. Right now I'm on Red Hat 8 desktop, and what we need now is a terminal where we can type in a few commands. And I'm going to go here to activities, select terminal, and it opens up this window. Now, to determine the kernel that is currently running on the system, just type uname -r, R for kernel release. Observe the case and spacing, then hit enter, and we get this output. But what does it tell us? This number here, 4.18.0, represents the base kernel release for software version. Red Hat 8 is based on Linux kernel release 4 point something, okay? 147 is the errata. It reflects minor enhancements, bug fixes, or security patches after the base kernel was released. EL8 is the source modifier, and it indicates where the kernel originated from. In this case, Enterprise Linux 8. And finally, x86_64 is the processor architecture this kernel is targeted for. The next thing we are going to see is the modules that are currently loaded, and to do that, just type lsmod and hit enter. Look at all these, so there are so many. Let me scroll up. We have the module, size, and used by. Tune tunnel, this is for networking. STP is, no, it's not what I thought it is. I thought it's FTP. Oh, I recognize one. XFS. This must deal with XFS file system that we will later cover. Let me plug in a flash drive with 3 partitions, one formatted FAT32, the other one ext3, and the last one NTFS, and see what modules will be loaded. Okay, I have attached the flash drive. To see it, let's go here to activities. At the bottom, show applications, all. Let's go into utilities and select disks. We have all these disks in the system, and here is our drive. As you can see here, it has the 3 partitions. This one is FAT, NTFS, and ext3. Now, something common to this and this first one and the last one is that they both say mounted. Mounted means you can access those portions of the drive. All you need to do is click on this link and it will take you right into the drive. Same case to this one. Click on the link and it takes you directly into the drive. That is for ext3 and FAT. However, something unusual about this drive is it is not mounted, meaning it's not accessible. No wonder it doesn't have a link here. And if you try to mount it by clicking on this one, mount, you get this error. Unknown file system, NTFS. Let's close that. This is because by default, Red Hat is not shipped with module for accessing this type of file system, although you may install it later. Back to the terminal, Typing lsmod again, we see additional modules. There is Ext24, which is backward compatible to work with the Ext3, and there is also vfat for accessing FAT file system. In our earlier results, close to the top, we didn't have such modules loaded. They come in just right here. Okay, we've talked about modules, and you may be left wondering, where are these modules loaded from? Well, they are physical files stored in the system. To see them, just go to Activities under Mozilla, click on Files. At the bottom here, go to Other Locations, select Computer, and into USR, lib, and here we see modules. Again, don't worry, we'll look at how to navigate your way within Linux. For now, let's go into modules. We have 2 directories. Let's select this one that matches our kernel release, and we see a bunch of files. Most of these text files contain metadata about modules contained in the kernel directory. They are a sort of table of content. We can click on one and see. Let's go into this kernel directory. Now, related modules are grouped together under one directory. Let's look around. The first one, architecture, KVM. There's nothing much in here. Let's go back to the top. Crypto. Here we see various modules used to implement encryption standards. There is Blowfish, DES, triple data encryption, MD4, SHA-512, Twofish. Okay, let's go back. Under drivers, these are hardware device drivers. And it has several categories. We can instantly recognize some, like Bluetooth modules, CD-ROM, there is FireWire, graphics processing unit modules. There is InfiniBand support for high-end computing. I think most of these modules are proprietary. We have network device drivers from different manufacturers. There's Amazon, Atheros, Cisco, Intel. Go back. Let's go into file systems. We see Safe Storage, Common Internet File System, CIFS, Extended File System 4. I bet Ext3 was loaded from here. You can imagine what will happen if you delete this one. Let's try open it. We can't open them to see the contents because they are usually in compressed format. GFS2, XFS. We don't see anything in TFS. No wonder we were unable to access the drive. Once installed, it should appear here. Remember, once the module is loaded, it becomes part of the kernel, having the same rights and privileges as any other kernel code. And therefore, it is important you keep an eye of where you obtain your modules. You don't just go to internet and download anything, since you may get pirated ones, although there are ways to keep this in check. Red Hat recommends that you obtain them from the assigned repositories. If you make a kernel modification that is not normally supported, you may end up damaging the kernel, and we usually call it tainting the kernel. Red Hat may or may not support you depending on the taint or its source. To determine this, let's go back to the terminal. I'll clear this and type cat/proc sys kernel tainted. A value other than 0 means our kernel is tainted, but in our case, it's all clean. The kernel is reliable. And the use of modules can only get you so far in extending the kernel. There is a limit, because there are other factors that will necessitate the revamp of a whole system. One major factor is the hardware upgrades. Like we are seeing rollout of 5G, DDR4, SSD, Bluetooth 5, 4K and 8K displays, multiprocessor chips, dense storage systems, GPUs, you name it. And a module may not be enough in this case. Another reason for upgrading the OS is provision or support of new services, since some services need to be interwoven directly into the kernel. And lastly but not least, all systems have faults, either at hardware or software level. Like sometimes back we saw Meltdown and Spectre. These were serious flaws in some microprocessors that would allow users to access private memory areas. Faults are discovered from time to time and patched up, sometimes requiring a system upgrade. And with that, we get to the end of this lesson. Thanks for watching. See you in the next video.